We shall understand joint and conditional probability, independent events, and Bayes' theorem in this module. We know that probability is used in almost every field of work, but what happens if some conditions are applied during the course of that work, or we have to deal with more than one factor at a time? This is where conditional probability, Bayes' theorem, and joint probability comes in use. Basically, this model focuses on the concept and applications of conditional probability, Bayes' theorem, and joint probability. Through this module, with the help of examples and figures, we try to relate these topics with the real-world scenario. While studying these topics, you will also get to know the following basic concepts of probability: addition rules of probability, multiplication rules of probability, mutually exclusive events, mutually exhaustive events, events with and without replacement, independent events, and finally conditional probability. Let us begin by understanding the additional rule of probability. Here, A union B denotes the event that either A or B or both occur when the experiment is performed. A intersection B denotes the event that both A and B have occurred. Addition rule in probability is a method of finding the probability of either or both of the two events occurring at the same time. Let A and B be two events in the sample space S. Thus, in the set theoretic notation, the union of events A and B is written as A union B, and the intersection or product of two events A and B is written as A intersection B. Moving on to the mutually exclusive events. If two events A and B are mutually exclusive, then according to addition rule, the probability that A or B will occur is the sum of each event, because two mutually exhaustive events are disjoint events and the occurrence of one precludes the occurrence of the other. Hence, A intersection B is equal to phi, the null set, which implies P of A intersection B is equal to 0. In a Venn diagram, two mutually exclusive events A and B may be represented as two non-intersecting circles as shown in the figure. In the figure, the two events A and B are disjoint, and hence, according to addition rule, the probability of occurrence of either event is the sum of each individual probability. Thus, in the set theoretic notation, the union of the events A and B is written as A union B, and the intersection or the product of two events A and B is written as A intersection B. The equation for the additive property is P of A union B is equal to PA plus PB. This equation of additive property of probability is postulated by the third axiom of probability. This additive law holds generally for any number of events. Thus, given n mutually exclusive events A1, A2, A3 up to An, we have probability of A1 or A2 or A3 or An is equal to probability of A1 plus probability of A2 plus probability of A3 and so on up to probability of An. Suppose further the given n mutually exclusive events A1, A2, A3 up to An is also an exhaustive set, that is, it covers the entire sample space S, then probability of A1 plus probability of A2 and so on plus probability of An is equal to probability of S, which is equal to 1. Let us understand it with the help of an example. A card is drawn at random from a deck of 52 playing cards. Find the probability that the card drawn is either a king or a queen. Let A be the event that the card drawn is a king and B be the event that the card drawn is a queen. Therefore, probability of A is equal to 4 by 52, probability of B is equal to 4 by 52, probability of A intersection B is equal to 0, since a card drawn which is a queen cannot be a king. Probability of A union B is equal to PA plus PB is equal to 4 by 52 plus 4 by 52 equal to 8 by 52, which is further equal to 2 by 13. Further, we shall discuss non-mutually exclusive events. If two events A and B are not mutually exclusive, then the probability that A or B will occur is equal to the sum of probabilities of each event minus the probability that both events occur together. Events are not mutually exclusive if they both can occur at the same time, that is, A and B overlap. The reason we subtract the joint probability when the two events are not mutually exclusive is to avoid the problem of double counting. In figure, the union of A and B is represented by the combined area A not B, A and B, B not A. The residual area then represents the event neither A nor B or not A and not B. By theorem of complementary events, we have probability of A union B complement is equal to 1 minus probability of A or B. Let us understand it with the help of an example. A card drawn at random from a deck of 52 playing cards. Find the probability that a card drawn is either a king or a spade. Solution. Let A be the event that the card drawn is king and B be the event that the card drawn is a spade. Therefore, PA, probability of A, is equal to 4 by 52, probability of B is equal to 13 by 52, probability of A intersection B is equal to 1 by 52, since a card which is a king and a spade is 1. Probability of A union B is equal to probability of A plus probability of B minus probability of A intersection B. This is equal to 4 by 52 plus 13 by 52 minus 1 by 52, which is further equal to 16 by 52 and equal to 4 by 13. Let us now understand the meaning of joint probability. Joint probability is a probability describing the probabilities of occurrence of two or more random events simultaneously. It is the probability of the intersection of two or more events. The probability of the intersection of A and B may be written as P A intersection B. In particular, if we have only two random variables, then it is known as bivariate probability. Understanding it with the help of an example. Find the probability that a card is a 4 and black. Probability of 4 and black is equal to 2 upon 52, which is further equal to 1 upon 26, since there are two black 4s in a deck of 52 and the 4 of clubs and the 4 of spades. Please note, joint probability cannot occur by happening of a single event, but by the occurrence of at least two events simultaneously. Moving on to understand the meaning of conditional probability. Conditional probability of an event is its probability of occurring given that another event has already occurred. If A and B are events in the same sample space, then the conditional probability of A occurring given B has already occurred is denoted by P of A slash B equal to probability of A intersection B upon probability of B for probability of B not equal to 0. Similarly, the conditional probability of B occurring given A has already occurred is denoted by probability of B slash A equal to probability of A intersection B upon probability of A for PA not equal to 0. From the above equations 3 and 4, it follows directly that probability of A intersection B is equal to probability of A that B has occurred into probability of B, which is equal to probability of B given A has occurred into probability of A. This equation states the basic rule of probability multiplication. According to this theorem, the probability of any two events A and B occurring jointly, that is, probability of A intersection B, is found by multiplying the probability of one of the events by the probability of the other, given the condition that first event has occurred or will occur. When the occurrence of one event is conditional upon the occurrence of another event, the events are said to be dependent events. Let us understand it with the help of an example. Food Plaza issued food vouchers to its regular 2,000 customers. Of these customers, 1,500 hold breakfast vouchers, 500 hold vouchers for dinner, and 40 hold both breakfast and dinner vouchers. Find the probability that a customer chosen at random holds a breakfast voucher given that the customer holds a dinner voucher. Solution. Let B be the event of customer holding breakfast vouchers and D be the event of holding dinner vouchers. Therefore, probability B is equal to 1500 upon 2000. Probability of D is equal to 500 upon 2000 and probability of B intersection D is equal to 40 upon 2000. Therefore, probability of customer holding breakfast voucher given that the customer holding a dinner voucher is probability of B slash D is equal to probability of B intersection D slash probability of D, which is equal to 40 upon 2000 upon 500 upon 2000, which is further equal to 2 upon 25. In the above example of the conditional probability, the sample sizes of the experiment are reduced to D, and hence the probability of B is not unconditional but conditional on given D. Now let's look at another example. Find the probability of getting a sum of 9 when two die are rolled, given when one of the die has at least one 3. The total sample space consists of 36 possible outcomes by rolling two die, which are 1 1, 1 2, 1 3, 1 4, 1 5, 1 6, and similarly for 2, 2 1, 2 2, 2 3, 2 4, 2 5, 2 6, and for 3, 4, and 5 in a similar fashion, and finally for 6 as 6 1, 6 2, 6 3, 6 4, 6 5, and 6 6. The probability of each outcome is 1 upon 36 since all outcomes have equal probabilities. Let A be the event of getting a sum of 9. Therefore, the possible outcomes are 3 6, 4 5, 5 4, and 6 3. Hence, probability of A is equal to 4 upon 36. Let B be the event that at least one die shows 3. Therefore, the total outcomes are 1 3, 2 3, 3 3, 4 3, 5 3, 6 3, 3 1, 3 2, 3 4, 3 5, and 3 6, which are 11 in number. Hence, probability of B is equal to 11 upon 36. Thus, probability of A intersection B is equal to 2 upon 36. Probability of A given B is equal to probability of A intersection B upon probability of B, which is equal to 2 by 36 upon 11 by 36, which is equal to 2 by 11. In other words, the assumption that one of the faces of a die is a 3 reduces the total possible outcomes to 11, of which only two outcomes, 3 6 and 6 3, are favorable to A. Since all 11 outcomes have equal probabilities, the probability of A under the assumption that B took place is 2 upon 11. Moving on to understand the meaning of tree diagrams. Tree diagrams is a pictorial way of solving conditional events. The following illustration will explain this method. A box contains 3 blue and 2 yellow balls. 2 balls are drawn at random. Through tree diagram, find the probability of the second ball drawn is blue given the first ball is blue. The second ball drawn is yellow given the first is blue. The second ball drawn is yellow given the first is yellow, and finally the second ball drawn is yellow given the first is blue. In the above tree diagram, it is clear that initially probability of B1 is equal to 3 by 5, probability of Y1 is equal to 2 by 5. Now if the first ball drawn is blue, then only 4 balls are left in the box, out of which 2 balls are blue, so the probability that second ball drawn is also blue is equal to probability of B2 given B1 is equal to 2 by 4. Similarly, probability of Y2 given B1 is equal to probability of second ball drawn is yellow given the first ball drawn is blue is equal to 2 by 4. Probability of Y2 given Y1, which is equal to probability the second ball drawn is yellow given the first ball drawn is yellow, is 1 by 4. Probability of B2 given Y1 is equal to the probability the second ball drawn is blue given the first ball drawn is blue is equal to 3 by 4. Thus, given this tree diagram, branch probabilities are conditional on the previous event. Moving on to contingency tables and probability tables. Joint and conditional probability can also be found out by contingency tables. Contingency tables and probability tables are useful in calculating the probability of joint events. Let's see an example to understand the concept better. The table below shows the contingency table for food restaurant. The price per veg burger is rupees 65 for McDonald's and rupees 55 for KFC. The price of non-veg burger is rupees 80 for McDonald's and rupees 95 for KFC. The contingency table of the prices of food restaurant mentioned in the previous example is shown in the table. The number of veg burgers in McDonald's is 65 and in KFC is 55, totaling to 125. Similarly, the number of non-veg burgers in McDonald's is rupees 80 and that in KFC is 95, totaling to 175. Studying the table horizontally, we have total number of burgers in McDonald's is 145 and that in KFC is 155. Thus, the total number of veg and non-veg burgers is 300. The contingency table is converted to probability table by dividing each of the entries in the previous table by the total rupees 300. The results are seen in table probability table for food restaurant shown. In this table, the joint probability for M and V, which is equal to probability of M intersection V, is equal to 13 by 60. M and NV is equal to probability of M intersection NV is equal to 16 upon 60. K and V is equal to probability of K intersection V, which is equal to 11 upon 60. K and NV is equal to probability of K intersection NV is equal to 19 upon 60. To find out the conditional probability, we apply the formula probability of A given B, which tells the probability of event A given B has already occurred, that is the joint probability of A and B divided by the probability of B. For example, probability of M given V is equal to probability of M intersection V given V is equal to probability of M intersection V upon probability of V. Similarly, all conditional probabilities can be found out. Let us now understand Venn diagram and conditional probability. Venn diagram is also useful in calculating conditional probability. In the figure, let A, B1, B2, B3 be 4 events in the sample space S. The entire big circle is the event A. Also, as we can see, B1 is a complete subset of A and a part of B2 is equal to B21 is within A. On the basis of the diagram, the conditional probability of A given B1, B2 and B3 events are as follows. Probability of A given B1 is equal to probability of A intersection B1 upon probability of B1, which is equal to B1 upon B1, which is equal to 1. Probability of A given B2 is equal to probability of A intersection B2 upon probability of B2, which is equal to B21 upon B21 plus B22. Probability of A given B3 is equal to probability of A intersection B3 upon probability of B3, which is equal to 0 upon B3 is equal to 0. Thus, we can see that as the condition of given events changes, the probability of event A also changes. Further, we shall understand the meaning of independent events. Two events A and B are independent if occurrence of A does not affect the probability of B occurring or vice versa. Probability of A intersection B is then equal to probability of A into probability of B. Symbolically, two events A and B are independent in a sample space S if and only if probability of A intersection B is equal to probability A into probability B. Hence, when the events are independent, to find their joint probability, multiply the probabilities of each event occurring separately. This is multiplication rule 2. Thus, A is independent of B if and only if probability A given B is equal to probability of A. Hence, the conditional probability of A given B has occurred, that is P of A given B, reduces to PA and vice versa. Let us understand the concept of independent events with the help of an example. A box contains 5 red, 4 green, 7 blue and 2 yellow marbles. A marble is chosen at random from the box. After replacing it, a second marble is chosen. What is the probability of choosing a red and then a yellow marble? Let A be the event of choosing a red ball and B be the event of choosing a yellow ball. Therefore, probability of A is equal to 5 by 18 and probability of B is equal to 2 by 18. Since A and B are independent events, their joint probability is the product of their individual probabilities, that is, P of A intersection B is equal to PA into PB, which is equal to 5 by 18 into 2 by 18, which is further equal to 5 upon 162. The experiment involved two independent events that occurred in sequence. There was replacement of the first item before choosing the second item. This replacement was needed in order to make the two events independent. Multiplication rule 2 can be extended to work for three or more independent events that occur in sequence. Two or more than two events are independent if replacement is done after each event. If replacement is not done, then the happening of next event becomes conditional on previous event. We shall now understand Bayes' theorem. Bayes' theorem is used for calculating posterior probability of an event from its given prior probabilities and conditional probabilities. It describes how the conditional probability of each of a set of possible events for a given observed outcome can be computed from knowledge of probability of each event and the conditional probability of outcome of each event. Let A1, A2, A3 up to AK be a collection of k mutually exclusive and exhaustive events with prior probabilities P, A, I, where I varies from 1 to k. Then, for any other event B which is known to occur as a result of the occurrence of the events AI, and for PB greater than 0, the posterior probability of AJ, given that B has occurred, is probability of AJ given B is equal to probability of AJ intersection B upon probability of B, which is equal to probability of B given AJ into probability of AJ upon sigma probability of B given AI into probability of AI, I varying from 1 to k, for j varying from 1 to k. It can be seen as a way of understanding how the probability that a theory is true is affected by a new piece of evidence. In other words, Bayes' rule can be applied practically in those situations in which an event can occur only as a consequence of the occurrence of one of the several mutually exclusive and exhaustive outcomes. Let us now understand Bayes' rule with the help of an example. Let A and B be two bags such that bag A has 2 white and 3 red balls. The bag B has 4 white and 5 red balls. A ball be selected and is observed to be white. Find the probability that B is selected. Let A1 and A2 be the two events given by A1, A is selected, A2, B is selected, and probability of A1 is equal to probability of A2 is equal to half. Let event W be the probability that white ball is selected. Probability of W given A1 is equal to 2 upon 5 and probability of W given A2 is equal to 4 upon 9. Probability of W is equal to probability of A1 multiplied by probability of W given A1 plus probability of A2 multiplied by probability of W given A2, which is equal to half multiplied by 2 upon 5 plus half multiplied by 4 upon 9, which is further equal to 38 by 90. Probability of A2 given W is equal to probability of A2 multiplied by probability of W given A2 upon probability of W. Probability of W is equal to half into 4 by 9 upon 38 by 90, which is equal to 10 upon 90. Thus, the probability that bag B is selected, given it's a white ball, is 10 upon 90.